Ariel Haziot.
Sorry for him.
Hello, everybody. Do you hear me?
Yes, we do.
Okay. So my name is Ariel Haziot. I'm working at CERN at the Magnet Group. And first, I would like to thank the organizer to give me the opportunity to present two projects that we have related to medical application in the Magnet Group. And also, I wish I could have been here with you, but unfortunately, it was not possible. So I do it remotely. So today, we'll present you two projects that we have. The first one, so-called Gateroid, is a novel magnet configuration that can be used for radiotherapy gantries. And the second one, called Fusilo, is a technological demonstrator of a compact curved dipole magnet. So I will go fast on this slide as they were already presented today and also by Ernesto just before. Just here to say that the message here showing those gantries is that they are bulky precision objects. They are very heavy and they need to move very accurately. And that's where comes the idea of Gateroid. So the idea behind Gateroid is to use axisymmetric field to bend the beam from any direction. And this uses toroidal magnets that are fixed and the field is in steady state. You can see here on this schematic the different elements of the Gateroid system. So there is a vector magnet that receives the beam from the accelerator and kicks it in different direction depending on the treatment. And then the axisymmetric field is bending the beam onto the patient, whatever the direction it comes from. If the axisymmetric field is tuned, we can also use this idea to focus a beam of different energies onto the patient. So in this case, the vector magnet is kicking at different angle depending on the energy. And then the beam is focused on the same location on the patient, whatever the energy used. So as you can see, there is no moving parts. So there is a very fast direction and energy switching that is possible with this system. And that makes it inherently conformal with flash capabilities, with multi-directional treatment and multi-energies. Yeah. Okay. Based on this concept, first system was designed for protons. As you can see, it's a very compact system delivering the beam from 16 different angles. And this system can accept protons energy from 70 to 150 MeV. So different energy can be used with the same system without changing the beam or moving any parts. And in order to do so, the magnetic field inside each of the magnet that you can see on this picture here is tuned. And that was one technological development that needed to be tested. So that's why we built a demonstrator of one of these magnets. So the demonstrator is scaled down by a factor 3, and but all the shape of the winding is exactly the same as in the design. You can see here the demonstrator magnet, and on the side, the fixing of the cover plate that holds magnetic sensors that will measure the field and validate the simulation. Here on this picture, you can see more detail on the fabrication. So the cable that we use for this magnet is a superconducting cable that is embedded into a copper profile in order to have more protection. And as you can see, the winding process is very simple. There is a spool with the cable. The cable goes through some kind of socks for the insulation. And then the mandrel turns here and allowing the winding of the magnet. And we put grade spacers that will shape the cable and so give the exact magnetic field that we want. The tests of this demonstrator were very successful. We measured the field profile at 10 different locations, actually 9 because one of the sensors broke down during the cooldown, and it was better than 1% compared to the simulation. And also the magnet reached the final performance without any quench or training, meaning that it's a very stable magnet. We use the opportunity of this test to also validate a full 3D model of the protection. And now we can trustly say that we are confident to say that we understand well the protection of this magnet, and we have confidence in the extrapolation of this protection to a full-size system. And here is just a picture of the team that worked on this project, and I'm thankful to all of them. From the design to the test, they did all a great job. In parallel to this demonstrator, more designs using the Gatorade concept were developed. This one was developed in collaboration with the Oxford University, and it's one that is dedicated to very high energy electrons of 200 MeV. The difference here compared to the previous design is first that it's a so-called superferic magnet, meaning that the field is mostly shaped by the iron that you can see here in gray on the picture, and the field is just generated by simple coils. And the second point of this design is that we do have the final bending magnets that were described before, but we also have a series of 3 quadrupoles that will allow to shape the beam during the travel. And finally, septum magnet here is here to amplify the kick given by the vector magnet. The vector magnet gives a kick of around 5 degrees, and this magnet here will amplify this so that we can have a larger bore for the patient at the end of the magnet, at the end of the system. And based on this design, we were then approached by the Queen proposal to produce gantry based on the category concept for it. So the Queen proposal is a proposal made in the Netherlands for the large-scale research infrastructure, and it aims to develop quench-free and energy-efficient systems for imaging and radiotherapy. And one of the working package, the working package number 5, includes the construction of a novel type of gantry system. And this will be built at Partrek, which is a proton research therapy center in Groningen. The system is a reduced version of the electron design, but for small, low energy protons, around 90 MeV, if I'm correct. And it has only 2 beam directions. So one that is coming from over the patient. Actually, those are not patients there, but more small animals and organs. But so one coming from the top and one coming straight. And the 2 beam direction can be switched in less than a millisecond. And that will be a validation that it's conformal with flash therapy with protons, for example. And the cost of construction of the whole installation will be around 4 million. And this is integrating as well fast CT, PET, and proton radiography. So in conclusion, the demonstrator test has shown that the magnet concept of Gatorade in the original materialization for compact proton is feasible and matches all the expectations. So there is no longer technological issue on the magnet construction. The main obstacle now for the Gatorade is to be accepted by the medical community. Gatorade is a very different system from the rotating gantry. It will change the treatment planning and it's not easy to accept, but it has unfair competitive advantage for flash capabilities that other gantries do not have today. And finally, the Queen proposal offers us the possibility today to realize a reduced scope but full-size prototype and to test it in condition. And this will hopefully bridge the gap towards the first medical realization for this concept. And to finish on the gantry, I would like to show you this video showing what could be treatment using the high energy electron design. So you can see here on the video the different parts of the gantry system. And it includes basically the beam coming from the accelerator, the vector magnet, then the first septum that is amplifying the angle, 3 quadrupole, and the main bending magnets. And the vector magnet is also a big innovation in the system because it's not moving neither. It's a rotating magnet that is always rotating. And then the beam shots are synchronized with the direction that we want to obtain. And this rotation is made in very fast, so we can very fast have different direction. And as you understood, the patient is placed in the middle of the bore of the bending magnet and then receive the beam from the different direction that are necessary for the treatment. And I think I have maybe a few minutes to switch on the Fusilo project pretty fast. So the Fusilo project aims to design, manufacture, and test compact curved magnet. So it has 3 Tesla in the central field, and it's bent over 90 degrees. So it's a quarter of an accelerator, basically, and over a small radius of 1 meter. And it has a very large aperture of 236. The project includes the main demonstrator that you can see here, but also few subscale that are here to validate the technology development. And it capitalizes on the CCT technology. So it's a way of making dipolar field using 2 solenoids that has been used at CERN for one of the magnet of the HLLHC project, one of the corrector. And possible applications are compact particle accelerators or compact radiotherapy gantry system, both in the medical field. The main design feature of this magnet is first a conductor that is with 70 insulated wires, meaning that we can produce high magnetic field but with very low current, only 300 amp. That means simple power converters that can be used and can be compatible with clinical installation. The correction in the winding allows us to tune a very homogeneous field over the whole aperture, and it's a very simple mechanical design, only few parts that are compatible with dry cooling system as well. You can see here the pictures of the fabrication of the subscale. So the winding, the insulation, the impregnation, and finally the magnet in the test station. As you can see, the winding is very straightforward once you have the former because you just insert your conductor in a groove, and so you don't have to really compact it or anything. And yeah, it's a very simple winding process. The test of the subscales were very successful. We powered them at higher current in order to reach the same condition that will be in the demonstrator, but in a smaller object. And both of them reached their nominal operation current and even the ultimate current. And they were showing good performance even at high ramp rate, so we could ramp them pretty fast. And the magnetic field inside was also in very good agreement with the simulation within 1%. And now we are ready to wind the final demonstrator. You can see all the parts are ready, including the mechanical structure and the magnetometer for measuring the field over the almost 2 meter long, 2 meter length magnet. And we hope to do a cold test early next year. And if successful, we could test this magnet in a beam setup as well. Thank you for your attention.
Very nice. Any questions? Can you hear me? Hello, can you hear me? Ariel, can you hear me?
Yes, I can.
So in your rotating magnet, what's the dose that you can deliver in one direction? What's the maximum dose that you can deliver in one direction?
The maximum what, sorry?
Dose, the maximum dose that you can deliver in one direction. So you have a rotating magnet, you can come from different angles. In one direction, what's the maximum dose that you can deliver? 5, 10, 20, 30 gray. What's the maximum dose?
Oh. Well, I'm sorry, I'm not sure I can talk about doses. I know that, for example, the proton system could deliver up to 250 MeV proton, but there is no limit in the dose because it's a steady state field, so we can
So how
keep.
protons in one pulse in one direction? Can you deliver 10 to 9 or 10 to 10 protons in one pulse?
Yes, there is no restriction in this.
Okay.
I mean, you mean in the if we consider the system with the rotating vector magnet, for example?
No.
Yes.
So in one single pulse, imagine a static magnet, then one pulse, one direction, how many protons can I give in one shot?
Well, this will depend on the source on which we are plugged in. So it's not. It really does not depend on this magnet, but more on the source.
So, no, there are no limitations. So basically, you can deliver, if you have 10 to the 10 protons out of your machine, you can deliver all the 10 to the 10 protons. There are no limitations in the gantry. Yes, sir. Hi, there's another question. In the conventional proton gantry, when you rotate the gantry, the assumption is that you should shoot into the isocenter with a precision of about 1 millimeter. So, and if not, there are some corrections done per each degree of the gantry position. How do you think in this magnetic gantry, which is really fantastic? Yeah, what would be the reproducibility of shooting with such a precision? Is it realistic to get such a precision?
Yes. So the first design that I showed, the compact proton design, this is part of thesis from Enrico Felcini that is now working at CNAU. And he showed in his thesis that we are reaching the clinical requirement. So we are within the 1 millimeter, and we can even do painting even in a small at a more accurate precision. So we know that we can design a field that is appropriate to those limits.
Any other questions? Okay. Thank you, Ernesto. Ariel, sorry.
No problem. Thanks to you, bye, Anna.
Thank you.